as an essential personality to the festival. Those contributions have become a staple to our efforts in promoting scientific literacy through this event. He is a physicist, head of the CERN Media Lab in Switzerland, and has been instrumental in implementing cutting-edge multimedia installations in science centers and visitor points from across the world. In the next enlightening hour during this time on stage, we will embark on a fascinating journey through the archives of scientific history. From ancient civilizations, cosmic perceptions, to the groundbreaking modern theories of Democritos and marvels at CERN, ladies and gentlemen, please welcome Mr. Joao Pequenao to explore how generations.
Thank you, everyone. Thank you all for coming. And I want to thank you all also for so warmly receiving me here in Hamburg. It's always a pleasure to be back. This is my third. So, I thought about doing something a little bit special for you today. The theme of the mela this year is make your own world. I mean, you say it differently in Urdu. Apologies, I don't talk Urdu. Make your own world. And I thought about talking to you about make your own model of the world. You'll see what that means in a minute. First of all, I think we should talk for just a couple of minutes about what is a model. What is a model? If you ask anyone in the street, hey, hello, nice to meet you. Can you tell me please what is a model? Well, a lot of people would answer something like this. These are models, right? You would call these models fashion models, but models, right? Why are they models? Well, they are models because they personify something. They give an example of what some fashion creator would like people to dress like, right? This is an ideal way to dress according to this idea. Well, this is also a model. This is a model of the Baghshari Mosque. It's a, well, you know architectural models. Why are they models? Again, because they represent something. They let you navigate through a concept of something using a simplified version of it, right? Here's another model. You know what is this? This is the school where we are. This is where we are right now. You know the name of this school? Crescent what? Crescent what? Model, right? It's a model. It's a model school. Why is it a model? I just had a charming discussion with the Crescent trustees in the back, which were telling me all the wonderful things about the school and why it is an example to follow. That's why it's a model, because it's an example. It's an idea, right? So let's say, to simplify, that a model is a representative concept of an idea. Or put it simply, you have some idea in your mind and you want to have a way to navigate mentally through it, so you create a model. That's what a model is. Now, I ask the question, if we can have a model of what the world is made of, that's the subject of this talk. What the world is made of, and if we can represent it through a model. We can ask this differently. What is matter? Because what things are made of is matter. What is matter, and what can be a model to explain it? Well, that's a very good question. Thank you very much. You know, these questions have been asked since a very, very, very long time. In fact, in the ancient world, and when I say the ancient world, so there were ancient civilizations in India, and by India I mean also the place where we are, in the broader sense, no offense. In the Greeks, you know, the Tibetans, they all had a same concept that there were basic substances, which were the substrate that constituted everything. Well, these substances, you probably heard about them, are earth, water, fire, and air. So according to this ancient conception, you can explain everything by mixing these four substances and, well, creating matter. It's made out of this. At some point, this guy, Aristotle, a Greek philosopher, one of the greatest thinkers ever to have existed, a guy that influenced countless generations in many different civilizations, including, you know, the golden age of Islam was strongly influenced by what this guy wrote. You know, he wrote about everything. He wrote about physics, about ethics, about aesthetic, about drama. And, okay, this guy had to write also, of course, about this problem of what is matter. So he accepted this concept of the basic substances. He called them elements, the basic elements. And he systematized it like this. So you can combine them to create matter. And the attributes of matter can be explained by what you mix in what proportions. So for example, if you get air and fire, you get heat. If you get air and water, you get wet. Earth and water makes cold. Fire and earth makes dry. Very simple. So this concept went forward for many, many centuries. And it was the basis of all the science which was produced even in the Middle Ages up to the modern science era, really, as you will see, with slight modifications. So there were fields like the field of alchemy, for the precursor of chemistry, which strongly supported themselves on this. Well, meanwhile, or actually a little before, there was another gentleman. His name was Democritos, another Greek, and he had this incredible insight. So he thought, no. Matter is not made just of substances. It's made of something, let's call them particles. Things which cannot be divided more. So the basic elements, well, atom, you know, in Greek, atom means indivisible. That's what it means. Atom means indivisible. So they are small hard particles. They are made of a single material. They are formed into different forms and sizes. They're always moving. It's dynamic. And they form different materials by joining together. This is the concept of Democritos. Well, you see these bullet points here, but let me illustrate this with an example. So, let's say that according to Democritos, you would like to describe what water is. Well, water looks like this. You see, atoms which are very round, and so they will flow easily in layers over themselves, and that's why water has fluidity. But something like iron will be like this. So the atoms are denser, and also they have spikes, which means that they will stick together. And by sticking together, they make a substance hard. This is a very interesting concept. However, it didn't really take off much. For over a millennium, people were more influenced by the ideas of Aristotle than Democritus. Democritus, by the way, preceded Aristotle by a tiny bit. Well, this was until this gentleman came around. This gentleman, John Dalton, was a chemist. And when I say a chemist, I don't mean just an alchemist. You know, there were alchemists in the Middle Ages. I know, like in Islam, you know, I'm Portuguese. I come from Portugal. Portugal is in what used to be Al-Andalus, you know, like the golden age of Islam. One of the places where it flourished was my home country. And one of the things for which Al-Andalus was known was by its scientists and its alchemists. And in fact, it had a big influence into the culture of my country later on. But I will be glad to talk in the corridors about it with you later on if you like. But meanwhile, John Dalton. So John Dalton resurrected the idea of atoms as you will see in a slightly more modern way. So for him, atoms were not exactly like the atoms of Democritos, but they still shared a lot in common. So they were indivisible small particles, like for Democritos. All atoms of the same element are identical, and different elements have different types of atoms, like Democritos. But then he introduced two novel concepts. One is that atoms can neither be created nor destroyed. So the laws of conservation, which are so dear for us in science these days, this guy introduced it. And another thing is that compounds are formed when atoms of different elements join in simple ratios to form compound atoms. In other words, this guy invented the concept of molecule. So, for example, a molecule of water, according to Dalton, would look something like this. So you have an atom of oxygen and two atoms of hydrogen. This is pretty close to the way we still represent molecules at high school or sophomore level. So with this that is here, you can actually do chemistry. You can do chemistry like we do today, almost. Anyway, always fine and dandy until came this gentleman, J.J. Thomson, another English physicist. Well, Thomson made an incredible discovery in the end of the 19th century. He discovered the electron. Now, you may notice this is a photo of Thomson in his laboratory, and there is a device in front of him. And this is the device where he discovered the electron. I will just for illustrative purposes, I will show you how it works, like very, very briefly. So you have two electrons, a plus and a minus, you know? And the minus, we call it a cathode. And he discovered that if you put very high voltage between the minus and the plus and a hole in the plus, that there are particles that cross it. And in the screen in front, you can see a beam. So there's something being emitted from the cathode. So we call this a cathodic ray tube. This, by the way, is the precursor of TVs for those that are older than 30 years old. You know that old TVs work with cathodic ray tubes. And so this guy discovered that for these particles that could be tilted, that trajectory could be tilted by magnets. So they were charged, negatively charged. Based on this, he made a new model of the atom. So the atom was essentially a positive mass with many negative electrons illustrated. He called this as a British name, a plum pudding model. You know, if it were Pakistani discovering it, he could have called it, I don't know, the Kheer with pistachios model, something like this, or the Chennai model, something like that, you know. But this guy is British, so he called it plum pudding model. So now you have an atom which is not indivisible anymore, which has particles inside of it. And okay, we could live with this until another English came along. It's always the English, right? You guys know it here in Pakistan. It's always the English. So Rutherford, he was a really brilliant guy. And he discovered many things, but two very important things. One was the discovery of beta radiation. I'm not going to give you many details, but what this means is that some elements, some atoms, spontaneously emit electrons. So you remember the contraption that our friend Thomson before the cathodic ray tube thing to emit electrons? Rutherford could do it just by having a radioactive element. Can we close the doors, please? There's a lot of noise. Thank you. So I was telling you, Rutherford discovered two things. One was beta radiation, and the other, which as you will see change the figure again of what an atom is, in the discovery of the atomic nucleus in the beginning of the 20th century. So, according to Rutherford, this is what an atom looks like. This is what an atom looks like. And you may have seen this image before. Oh, I see that now the mic works. Was not working before? All right. So, some takes from this model of the atom. The first is that now, most of the mass of the atom is in a nucleus, in the center, which is positively charged. And the electrons are turning around it in orbits. So this concept of orbit, too. So they're not static anymore like in the plum pudding. They are now dynamic, going around the atom. You probably have seen variations of this, like this. Okay, this is a very common representation of the atom. If you go online and search for images of an atom, you will see something a little bit like this. What is different here is that here there are neutrons. Well, in the time of Rutherford, when he made his model, neutrons were not discovered yet. It was just in 1932 that another English discovered neutrons. But I have to say one thing before I proceed. I have to give credit to the power of this idea, of this representation of the atom. You see, this image is inaccurate, but it's so powerful that I'm sure that we have seen it everywhere. Like, for example, even the experts are using it. This is the logo of the Pakistan Atomic Energy Commission. Notice something there? Rutherford atom. These guys are the experts. Some are sitting here. These guys are the experts in nuclear physics. And they use the Rutherford representation of the atom. But they are not the only ones. Look at this. Pakistan uses it. The USA, Bangladesh, Saudi Arabia, Jordan, these are atomic energy commissions all over the world. And the symbol that we have for the atom is the Rutherford atom for all of them. Why? Because it's such a powerful symbol. It's so attainable. You can see right away that an atom is made out of electrons and the nucleus, positive nucleus, and then, the nucleus has other things inside. Anyways, anyone can identify immediately this as being an atom. But I digress. So, in the beginning of the 20th century, the panorama of our knowledge had changed dramatically. By then there were 4 new fields that appeared and that marked all the science and technology of the 20th and part of the 21st century. These were nuclear physics. So now we know that atoms have a nucleus. We can try to combine them, break them, and so on. Nuclear physics. These were quantum mechanics. So we learned that the rules of nature at a very small scale are different from the rules at our scale. They obey to quantum mechanics, they are quantified, quantum mechanics. Then of course particle physics, now we know that there are particles. They are not just atoms, they are particles. And we can play with them, we can try to determine what their dynamic looks like. That's particle physics. And there's relativity. There's special relativity, general relativity, but relativity. So these 4 fields mark the 20th century physics. And so, I have to talk about this gentleman. Because one of his achievements is crucial for the rest of the story I want to tell you. Paul Dirac, another British. Paul Dirac was a genius. Among other things, he created the so-called Dirac equation. Don't worry, I'm not going to try to explain it to you. I just put this in very simple terms. This puts quantum mechanics and relativity together to try to explain the dynamics of an electron. Here's the problem. He got this equation, and when he tried to solve it, he saw that there were 2 solutions for the electron. He was expecting to find one solution for the electron, and he said, well, there are 2 solutions. And worse, these 2 solutions, one looked exactly like the electron, which was already known at the time. So the electron has a negative charge and a spin up. I have to do a little parenthesis here. In quantum mechanics, we have these numbers which are called quantum numbers. Okay, quantum numbers are quantities which are used to characterize a particle. Let's say all of you can be characterized by a series of numbers. For example, your height, the length of your arm, the distance between your eyes. I wouldn't say your weight because that varies a lot. But say all these values could determine biometrically who you are, right? So particles, they also have a series of numbers which are unique for each type of particle. And we call these quantum numbers. They are quantified. There's not a spectrum for them. They are fixed numbers, they are quantified. Okay? So spin is one of these numbers. And I close my parentheses here. So, you found Pauli, we were on Pauli. Pauli found two solutions for his equation. One described exactly an electron as was known by them. Spin up, negative charge. The other, described a particle which had a positive charge and a spin down. It was like the mirror image of the other. The quantum numbers were inverted. So he called this particle the positron. And two major implications come from this. The first is that Dirac described for the first time what is an antiparticle. So we have particles so far, and now we have mirror particles, big particles which mirror these quantum numbers that characterize them, and these are antiparticles. Okay, so this huge revolution. Okay, and the other is that he predicted a particle before it was observed. So the positron was finally discovered in 1932. So, but it was predicted before it was discovered. This is huge, because from this point on, we know that we can keep discovering quantum numbers, adding them to the equations, and we will be predicting new particles over and over and over. Now, my talk is not about an exhaustive history of each particle which was discovered. That will be boring. I want to jump right to, the new experiments which were built meanwhile, and how they change our way to make discoveries. So, again, the quest that we have is to create a model to explain matter. Remember, this was from the beginning. This is our puzzle, to try to explain what matter is. And so, once we knew that this was attainable, major laboratories were created worldwide to study what is matter and the origin of the universe. And here I'm going to do a huge jump, and I would like to talk to you about my organization, CERN. So CERN is the world's largest particle physics laboratory. So the main purpose of CERN is really to try to find out why matter is what it is. But in fact, we have 4 missions. Well, the first mission of CERN is, of course, advance the frontiers of knowledge. So, make discoveries, help us understand better the universe. But it has other missions too. Of course, technology, innovation. Because, to develop all these we have to develop lots of technologies and devices to make these discoveries, making experiments. Then, of course, there's an educational mission as well, to train future scientists and engineers, and even current scientists and engineers, and even general public, such as yourselves. That's a very important part of our mission, and one that I personally take very seriously, and this is also one reason why I'm very proud of coming here to see you in Lahore, is unite people from different countries and cultures through science. This is very important, especially in the troubled times that we are going through today. So, a little idea of how CERN works in terms of structure. So it's an international organization. Think about, for example, the United Nations, right? But our focus is science. So we have member states, 23 member states. Then there are 7 associate member states, including Pakistan. You can reserve your applauses for the next slide. You'll see why. Then there are 3 associate member states in the pre-stage 2 membership. So these are countries which will become members very soon. And then there are observers to the council. So there's a council that manages all the operations. Now, I told you Pakistan was an associate member state. And I would like to tell you a little bit about that. So Pakistan became a member state, an associate member state of CERN in 2015, but much before there were already association agreements between some institutions in Pakistan and CERN. And of course, very high-profile politicians have been at CERN, and of course, CERN diplomats in Pakistan to seal these agreements. But I have to emphasize one thing. There is an organism in Pakistan which manages this relation, is the custodian of this wonderful collaboration, which is the Pakistan Atomic Energy Commission. And you may have noticed that they have a very big stand right by there. So there's a picture we took there just yesterday. So some of the members of the PAC, including Dr. Zafar Yassin, who's sitting right here, and is the Pakistani representative at CERN. So if you would like to know more about the participation of Pakistan at CERN, or if you would like how you could contribute to the projects that are ongoing at CERN, these are the people you should go talk to. They have a stall right there. They will be very happy to talk to you. In fact, Dr. Yassin yesterday gave a talk exactly about that, about opportunities for Pakistani nationals at CERN. So please go and talk to him. And now you can applaud them. There's something else about the relation between Pakistan and CERN. You may recognize this gentleman, or maybe not. That's Antunes, one of the great scientific minds of the 20th century, a major particle physicist. One of his great contributions, not the only one, but one of his great contributions was what we call electric unification. I'm not going to explain to you what that is. What I'm going to explain to you is that it's so important that it merited him being awarded the Nobel Prize of Physics in 1979. But that Nobel Prize of Physics was attributed because his predictions were confirmed by an experiment at CERN. You see, this is how it goes. Theoretical physicists make predictions, make models, but then models are just conjectures until you are able to actually validate them experimentally. And this is what happened here. So a beautiful example of how theory and experimentation go hand in hand is Antunes. By the way, little parenthesis, my former laboratory at CERN used to be on the street Salam. There is a street, Abdul Salam. At CERN, all streets have the name of physicists. And just a coincidence that my laboratory was in Salam. So, let's go again to our question of what is the universe made of. So by the 1970s, we already had a good theory of the fundamental forces. You know, meanwhile, we made lots of experiments, we discovered new quantum numbers, we saw how things would play along together, and there was a beautiful model, again, a model in a sense of a representation of what something looks like. Beautiful model that describes this, we call this the standard model. And this model was the main motivator for particle physicists in the decades after the 1970s, trying to validate it. So it all made sense on paper. But is it true? So we need to make experiments to find it out. So how do we do experiments? So, me go there by a little side road. So you have matter at our scale, and of course you can have matter at the molecular scale, at the atomic scale, then you can go deeper in, there's the nucleus, and the nucleus is made of, as you know, protons and neutrons, we call these nucleons, and even those are made of something, we call these quarks. And you can try to see small things using a microscope, okay? But how do you use a microscope to see very small things? So there is this relation called the Planck-Einstein relation. Basically what it means is that all particles at a certain energy have a wavelength, okay? And the wavelength, that's lambda there, is inversely proportional to the energy of this particle. So if you accelerate the particle, if you give it energy, it starts vibrating in a certain frequency. If you give it more energy, the frequency is higher, or the wavelength is smaller. Okay? So, if you want to look at something with visible light, which has a certain wavelength, so the wavelength gives you the limits of what you can see. So it's in the order of this wavelength. So with the visible light, let's say you put some blood in the microscope, you will see something at the scale of a red blood cell. If you use more energy, like X-rays that have more energy and so a smaller wavelength, we'll be able to see a lot more detail in this blood cell. You see something like this in an X-ray microscope. But what if you want to look at the scale that we're talking about there, of atoms and nucleons and even quarks? You need a super microscope. So remember the Planck-Einstein relation. To get the very small wavelength, you need a lot of energy. So the super microscope that we have at CERN is called the Large Hadron Collider. So it's a particle accelerator that accelerates particles with a lot of energy. And so we can really see matter at very, 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 very small scales. So a couple of words about the Large Hadron Collider. So it's the world's largest particle accelerator. It's about 27 kilometers in circumference. It crosses the French-Swiss border. Okay? So for you to have an idea, again, this is a map centered here, where we are, at Crescent Model School. If it were centered here, this is what it would look like, the circle that we have there in the screen. Very big. So, I'm sure you are wondering, so if I would go down there, what would it look like? Well, that's a very good question. That's what it looks like. So this was a friend of mine that went down. I went down there many times. So on a bike and filming it. So it's an exchange of tubes over and over and over, but these are not just tubes. These are very high-tech devices. In fact, the whole set of the devices that go into the LSC is most probably the most complex scientific project ever made by mankind. More than the Apollo program, you know. So, it's this endless set of tunnels with these modules there. And what do they do? Well, what we do in a particle accelerator, like I said before, is we accelerate particles, like the name says, right? So we accelerate them at very, very, very high energies. We don't talk about speed, we talk about energy. But if you want to talk about speed, this is literally like a bike ride away from the speed of light. Put it like this. So they got very, very high energies, and the system is conceived to make them collide at 4 precise points. And in these points, we build detectors to detect what comes out of the collisions of particles. Now, you may be asking, what's inside these detectors? And so I invite you to make an experiment with me. Would you like to make an experiment here? Yes. We are going to become a particle detector here in the room. Are you up for that? Yes. All right. What color is this? Red. Okay. What color is this? Blue. Blue. Very good. center now. And you see the camera here and me? So the people on the right-hand side, from your perspective, whenever you will see the color red, I want you to clap. Not the people on the left, on the right. The people on that side will clap. The people on this side will clap when they see blue. Is that understood? Yes. So, you clap when you see red. You clap when you see blue. All right. No. One clap. One. So, what we did here was that you were able, as a group here, to act as cells in the detector, and you reacted to different wavelengths of the light that came from this screen. Of course, each one of you has a brain and an eye, but that's what happened. So a detector, a particle detector like the ones that we use at CERN, well, is something like this. This is the Antunes experiment. This is the biggest of the 4 detectors. We call the detectors experiments. The biggest of the 4 experiments that are in the course of the LSC. So it's 25 meters high by 44 meters long. The cavern where this is the size of a big mosque. I say cathedral usually in Europe, but we get the idea. And as you can see by these labels there are many subsystems different. So each of these subsystems is tuned to detect something a little bit different, using different methods. A little bit like the way you detected differently red or blue. So these different subsystems are tuned to detect different things. And when we put all of this together, we obtain a device that is like this. So this is footage from another detector. This is the CMS detector. It's a little bit smaller than the Antunes detector, which we were seeing before. Actually, this is Antunes. I used to work on this experiment a long time ago. So you see, like you see the truck like carrying to the street these gigantic pieces of it, and then so there is this pit where these gigantic parts that weigh sometimes hundreds of tons are lowered. So the whole thing weighs 70,000 tons. Okay. So you see the scale of like the tiny humans. So the physicians and the engineers, physicists and engineers working on this. And so each of this is CMS. This is another detector. Pakistan has a good participation of researchers in these experiments, CMS. Again, go to the stand of the Pakistan Atomic Energy Commission and ask them. Some of the researchers working on this precise detector are right there, and we'll be happy to talk to you. Anyway, so this is what a detector looks like. And I would like to show to you now the whole process from the acceleration to the collision, how it happens. So, in fact, before the Large Hadron Collider, there's a series of accelerators that lead to it. So protons are pre-accelerated, and then they are injected in the Large Hadron Collider. And of course, if we would go inside the tunnel, and we go along the accelerator, and then if we even go inside the accelerator to see what's happening, we see here's a proton. In reality, they are not like this. There's bundles of billions of them, and there it goes, and it's approaching the Antunes experiment. There's another coming from the other side. They're gaining speed. The distance is smaller and smaller, and they are approaching and they collide, and there is a collision. And you see this fluff ball, these straps that are here, and so it looks like something like this. But what the heck is this? What the heck happened here? Well, what happened here, ladies and gentlemen, is something absolutely incredible. It looks like magic. It's not magic, but it looks like magic. I'll tell you why. You certainly know the most famous physics equation of the 20th century, right? Yes. It's written right there. What is it? E equals mc squared. What does it mean? Energy can be converted into mass. That's a simple way to put it. I like to put it like this. Think about water and ice. Water and ice is the same thing, right? But in a different state. Now, think about it like this. Energy and mass are the same thing in a different state. So you can transform energy into matter, meaning particles, or matter into energy. There are rules for that. I'm not going to talk about them now. If you want, on the side, I will be very happy to explain the rules to you. But basically, that's what happens. So, when we give lots of energy to the protons, in the moment of the collision, by the amazing power of E equals mc squared, the energy that we gave them materializes into new particles. You see, energy becomes matter. So what you're seeing there, these tracks, these are not the bits and pieces of the protons that we broke apart. No. These are new particles which did not exist before. And that reproduce about 1 billion times a second. It's pretty amazing. That's why I said it's almost like magic, because we are creating something new all the time. And we don't know what is coming out of there. That's the fun part about it. We don't know what nature is going to give us. So, energy becomes new particles, and then we have to try to figure out what is it? I like to use an analogy to explain how we look at the characteristics of what we observe and how we interpret them. This is the blind scientist's analogy. Imagine the following thing. 6 scientists are given the task of identifying an object in front of them. But each of them sees a different part of the object. They are blindfolded. They don't see. They just see, so they just feel the part that is immediately in front of them. So there is one that feels something sharp and hard and says, ha, it's a spear. There's another that sees something that is very elongated and that tilts, it's a snake. Another one is, oh no, there's something here that is solid and that is right to the ground, and it's around the right diameter for me to say confidently, it's a tree. Another that is, no, there's something that they can move around and it blows away wind, so it's a fan. And another says, no, it's something big and really vertical, and solid. It's certainly a wall. And yet another says, no, come on guys, I can feel it, it's a rope. What is it? Yeah, it's an elephant. So, to have the full picture, we have to analyze all the data, all the aspects of what our sensors are showing us, and then put it in perspective. You cannot just observe something here and right away to the conclusion. You need to keep getting data and then try to make sense of it as you go along. So, I'm going short to the end of my talk. So this is about the time. Again, this is not a technical talk. This is just a fun and introductory talk about our models of the universe. So I would like to go straight to it. And ladies and gentlemen, I would like to introduce to you the standard model. the standard model of particles. So, after all of this, after the model of Democritos, and after Thomson made his plum pudding, and after the Rutherford model of the atom, which even the professionals are using in their logos, after all these other particles that we follow around and these forces, what do we think today that matter looks like, that the constituents of matter look like? So this is the standard model, with the standard model. So we have here 4 blocks, as you can see. So we have on the upper left quarks. Quarks are heavy particles that constitute, among other things, the nucleons. The protons and neutrons are made up of quarks. In fact, just of 2 of them. Then you have leptons. That's another family. These are families of particles. Leptons, like the electron, for example, and all the others are cousins of the electron. Let's put it like this. And then you have, on the right, the forces. So the forces, they need an intermediary, a carrier particle. So we call these carrier bosons. So they are on the left. And then there's a special particle in the center, about which I will not talk about now. It's not the scope of this presentation, which is the Higgs boson. Now, this is a standard straight image to talk about the standard model, but I like, maybe don't tell my colleagues at CERN, but I kind of prefer this one. I find it very elegant. Because you really see the quarks in one side, the leptons in the other, the relation with the carriers of course, and the Higgs boson in the center. It's a very explanatory image. Of course, there's another way for me to show you the standard model. That's a little bit more abstract, but I find it beautiful. Which is this one. So this is the great physicist, John Ellis from CERN, writing on his chalkboard the equations of the standard model. I mean, if you want to see what it looks like this. So, in a nutshell, did you notice this is my t-shirt? Yeah. I'm carrying the standard model with me all around. In a nutshell, this equation is an abbreviated version of the true one. The full form one is like 27 pages long. This is a compressed version of it. But all we know about particles and forces is synthesized in this equation. That's the power of mathematical abstraction and modern models of physics. Now, I just want to end with one simple mention to the fact that we know very well that the standard model, as beautiful as it is, as experimentally confirmed in many aspects as it is not, I repeat, it's not the definite answer to what matter is like. There's a lot more, and we know it. We know it. It's just that we are, I don't want to say clueless, but kind of, you know? Right now, we know that there's a few things that we cannot explain with the standard model, but we don't have any better model to replace it. So, a big part of the work of physicists worldwide, and particularly at CERN, my organization, with the colleagues from all around the world, including in Pakistan, is to try to find out what is it that is missing here, and that can allow us to explain the other phenomena that don't fit in here. And with this, I end my presentation. I'll be happy to answer two questions and to talk to you outside, on the side of the room.
I'm on the behalf of the people. I think people will be hesitating or questioning because of the language barrier. And I was thinking if...
Apologies for that, my Urdu is very bad.
तो मैं सवाल उर्दू में करता हूँ ताकि बाकी जो है ना उनको भी पता चल जाए कि हम किस बारे में बात कर रहे हैं. तो यूजली ये सोचा जाता है जब भी सर्न का नाम आता है कि सर्न जो है वो ये फाइंड आउट करने की कोशिश कर रहा है कि बिग बैंग से पहले क्या था, या यूनिवर्स जो है उसकी क्रिएशन कैसे हुई. आपने जो बताया है कि सर्न क्या काम कर रहा है, तो इट फील्स लाइक अ कवर ऑन द इंटेंशंस एंड व्हाट यू आर डूइंग.
So what he's asking is that CERN claims that it's working on to find out what happened at Big Bang and before it, what existed. So the work that CERN is doing, is it really correlated to that, or is CERN trying to do something else under the cover?
Okay, the short answer is no. We are not trying to investigate what was before the Big Bang. In fact, no offense, but I'm not even sure that the question makes sense in the sense, with all respect, with the sense that it is very possible that the notion of time at the moment of the Big Bang didn't even exist. So, in other words, the clock started not on zero, started already some time ahead. Now, about the Big Bang, yes, a big part of our research is focused on researching the origin and evolution of the universe. Absolutely. Not before the Big Bang. But let me tell you how that happens, if I may, because maybe that answers the question of someone else. Imagine, so the Large Hadron Collider is a little bit like a time machine, okay? But not a time machine in the sense that many people think, like I enter inside some device, I press a button, and I'm surrounded by dinosaurs. That's not how it works. It works like this. Imagine you see a picture of your grandparents, okay? And you see that they had some physical characteristic that you can see yourself. Let's say you have, I don't know, you have a birthmark here. You don't, but just bear with me. And you see, wow, your grandparents already had that birthmark. So you know where it comes from. So if you could look at a picture of your ancestors, you are traveling back in time. Because you are having a snapshot of what time was like before, right? So what we are doing is we are getting snapshots of what the universe was like before. We are recreating conditions very close to the Big Bang, slightly after, not before. And by doing that, we are looking at our matter ancestors, in a sense. And we are studying their properties, and we can see also how they relate to how we perceive matter now, in the current state. Does that answer your question?
Thank you.
So I have a question about the practical implications of the work that is being done.
Yes.
The practical applications. So because current nuclear fission technology is based on the standard model and separating neutrons and all that. So, but does this bring more efficiency to the process, or there is no?
What process?
Fission, the nuclear energy. Is it going to make it,
okay.
Or is it going to change it completely?
All right. If there are interesting applications, if I may paraphrase your question is if there are interesting and useful technological applications of what we are doing at CERN. Can I paraphrase your question like this? Thank you. So many. I could give another talk just on that. I won't, don't worry. First of all, there's a lot of things that we use every day that you may not know, but they came from the research right at CERN. There is one, for example, that I'm sure you used already 10,000 times today, which is the World Wide Web. Maybe you don't know, but the World Wide Web was created at CERN. Originally, it was a research project to put together different networks of computers, which were before this wasn't possible. So that's one that we like to quote. But there are so many, like medical applications. Both, you know what? I will give you a short answer. But if you want a longer answer, I really invite you to go to the stand of the Pakistan Atomic Energy Commission, because they actually have lots of things going on, practical, and happening in Pakistan. And if you would like to get involved on that, they are the people you should talk to. But let me just tell you one thing, and I'm not evading your question. Imagine that in the beginning of the 20th century, remembering my talk, like with the forefathers of quantum mechanics and all that, imagine you would ask them, okay, this thing, quantum mechanics, it's all fine and dandy, but what good is it for? What can I do with it? And today, you have a supercomputer in your pocket, I'm sure. Everyone here has. And this thing would not work without quantum mechanics. This thing, the GPS here, would not work without relativity, you know? But if you ask the people that created it originally, that created quantum mechanics, relativity and all that, they would not know how to answer to you. Because they were doing fundamental research like we are at CERN. Fundamental research means we're trying to find out why nature is the way it is. You are not trying to find out applications, but they will eventually.
First of all, thank you so much for the wonderful talk. And my question is related. Can you hear me now?
Yes.
All right. So first of all, thank you for the wonderful talk. And my question is related to quantum computing. So you were talking about the opportunities available at CERN, and unfortunately I wasn't available yesterday for knowing about the opportunities. And basically, when we think about CERN, like in the presentation, we have all this fancy hardware for doing fundamental research on particle physics. But granted that Richard Feynman, when he envisioned quantum computing, he had the fundamental idea that one day we will probably be able to simulate the natural phenomena that we have to emulate on a classical computer. And granted that there is an aspect of quantum computing, that is quantum simulations, that is focused on that, specifically that, and generally quantum computing. Are there any opportunities related to that at CERN?
Absolutely. And again, I will talk to you generally, but I see Dr. Zafar Yassin gesticulating because I think you guys want to talk to each other after, but shortly, there is a quantum computing initiative at CERN. That's what we wanted to talk about, right? Yes, yes.
And they are also asking
I'll pass you the microphone. Dr. Zafar Yassin is the representative of Pakistan at CERN.
आपका क्वेश्चन था, मैं बताऊंगा कि जो क्वांटम कंप्यूटिंग है CERN में दो तरह की है। जैसे अभी जाओ ने बताया था कि क्वांटम कंप्यूटिंग इनिशिएटिव उन्होंने शुरू किया QTI से, उसमें हमारी मीटिंग हो चुकी है और अभी हम दो लोग पाकिस्तान टर्मिनेटिंग कमीशन से, एक निगोब से और एक प्यास से भेजना चाह रहे हैं एज ए फर्स्ट स्टेप पे। फिर हम उनके साथ एक एडेंडम भी साइन करना चाह रहे हैं। जब थोड़ी सी चीज़ें आगे बढ़ेंगी फिर दूसरों को भी इन्वॉल्व किया जा सकता है। और दूसरा एक ओपन क्वांटम टेक्नोलॉजी है उनका, जो कि पूरा यूरोपीय यूनियन का था, उन्होंने गवर्नमेंट ऑफ स्विट्जरलैंड को दिया, वो भी CERN को देना चाह रहे हैं। तो ये चीज़, दूसरा जो क्वेश्चन था मैं थोड़ा सा उर्दू में एक्सप्लेन कर दूँ, जो एक टाइम वाला था, तो जो कि मैं एक्सप्लेन करता हूँ उधर भी चीज़ों का कि जो CERN है, ये बिग बैंग की बात करते हैं कि वो कैसे उनको ओरिजिन ऑफ यूनिवर्स फाइंड आउट करता। तो आपको पता है कि जब बिग बैंग हुई थी, अभी हम जो एटम्स देख रहे हैं, एटम किससे मिलकर बनता है? ये प्रोटॉन्स और न्यूट्रॉन्स। और न्यूट्रॉन जो है तीन पार्टिकल से मिलकर बनता, तीन क्वार्क से। जो प्रोटॉन्स है वो भी तीन क्वार्क से मिलकर बनता। तो जब बिग बैंग हुई थी, बिग बैंग के फौरन बाद वो न्यूट्रॉन और प्रोटॉन नहीं थे, बल्कि क्या था, वो क्वार्क्स और ग्लूऑन्स थे। जाके क्वार्क्स और होते सारे थे। अब एटम को तो हम तोड़ सकते हैं, जैसे एटम से हम इलेक्ट्रॉन पैदा कर सकते हैं, एटम से हम प्रोटॉन पैदा कर सकते हैं, एटम से हम न्यूट्रॉन पैदा कर सकते हैं। लेकिन हम प्रोटॉन को नहीं तोड़ सकते। प्रोटॉन से हम तीन क्वार्क्स को पैदा नहीं कर सकते, न्यूट्रॉन से हम तीन क्वार्क्स को पैदा नहीं कर सकते। तो ये जो आप लोगों ने आज बड़ी मशीन देखी है, लार्ज हैडरन कोलाइडर, जब हाई एनर्जी के प्रोटॉन आपस में टकराते हैं एक इस तरफ से एक इस तरफ से, तो वो फिर प्रोटॉन नहीं रहता, प्रोटॉन की टूट जाता है क्वार्क्स में। फिर वो वही कंडीशन, वही मैटर बनता है जिसको हम क्वार्क बोर्न प्लाज्मा कहते हैं, जो आफ्टर द बिग बैंग। तो फिर हम उनको सर्च करते हैं जैसे अभी, और वो जो उसमें इस किस्म के पार्टिकल्स होते हैं उनको हम डायरेक्टली हम डिटेक्ट नहीं कर सकते। उनका जो टाइम स्केल है 10⁻⁻³ सेकंड होता है। और अभी तक कोई भी ऐसी मशीन दुनिया में नहीं बनी, कोई भी ऐसा डिटेक्टर नहीं बना जो उनको डिटेक्ट कर सके। अभी तक जो डिटेक्टर्स बने हैं वो डिटेक्ट कर सकते हैं पार्टिकल को 10⁻⁹ या -11 सेकंड की रेंज में। बल्कि जाओ ने जो दिखाई थी वो जो पार्टिकल जिसको उन्होंने मैजिक का नाम दिया, तो वो उन्हीं मैंने इसी वजह से कहा था कि वो वही पार्टिकल थे जो आफ्टर द बिग बैंग वाले पार्टिकल्स थे, लेकिन उनका टाइम स्केल बहुत कम होता है और उनको हम डायरेक्टली नहीं डिटेक्ट कर सकते। वो उसके बाद दूसरे पार्टिकल बनाते हैं उनको हम डिटेक्ट करते हैं।
जब हम उनको डिटेक्ट ही नहीं कर सकते तो हम कैसे कह सकते हैं कि
नहीं, वो रिवर्स इंजीनियरिंग करते हैं ना, जैसे उन्होंने एग्जांपल दी थी कि आप अपने दादा परदादा के ऊपर तेल था, रिवर्स इंजीनियरिंग से जाके
I just wanted to explain the experiment you were talking about.
I'm sorry, I can't hear you well.
Yeah, sorry, you were talking about the experiment where you had a circumference of 727 meters. The reason I'm asking you this question is that 10 years ago when this experiment was happening, we had a discussion in Leicester University and there were some interfaith people who would not understand the scientific language and they wanted to know more about how
I'm sorry, did you not understand what?
the scientific, like we are not physicists.
Yeah.
I also study physics and GCSEs, not beyond that, but I'm really interested in that. But I would love to know how would you explain this?
I couldn't hear you.
Yeah. How would you explain this experiment in a layman's perspective or in a layman voice? Some people would like to know what was this, because the concept of fission and fusion and what was actually happening, where actually was that...
You mean explain the accelerator?
Yes.
If I have time, I do it right now for you in 2 minutes. Would you like to?
Sorry?
If I have 2 minutes, I do it right now for you here.
Yeah, thank you very
Do I
much.
have 2 minutes? No. You say no. I'll do it outside.
Okay, that's fine.
By the way, I try to make it accessible. I try to make it non-technical, accessible. But I can give you an amazing analogy for how it works. I'll do it outside.
Okay, that's fine.
Thank you very much. That's all the time we have. Cheers.